Welcome back to the series of talks on pedigree polytopes. In the last session, we discussed what is a pedigree, we defined, and then you also did an exercise. In this session, I'm going to talk about pedigree optimization problem. That means we are going to define an optimization problem over the set of pedigrees. And so it's a combinatorial optimization problem, and I'll describe that soon. Given n greater than 3 and the cost function from delta, the set of triangles, to rational numbers, we define the cost of a subset P of triangles as C of P equal to sum of C of U for all the U in P. That means that the total of CU for U belonging to P. Now, once this cost function is defined like this for any subset, we can now define the pedigree optimization problem. Consider the directed graph D, delta A, as defined earlier, where A is the collection of UV such that U is the generator of V. And C is given as above. Our job is to find P star, a pedigree that minimizes C of P over all pedigrees in D. So that's the definition of this pedigree optimization problem. So from the set of triangles, which are a set of triangles, we select a subset which is a pedigree, and among the pedigrees we are selecting the best one according to the criterion C. This is the main problem of our interest. So up to now you wouldn't know why I define pedigree or why we study this problem. So I can't keep you waiting. So I will explain what is the motivation for studying this problem next. So, what is the motivation for studying pedigrees? So you have been waiting for that. I'm going to explain that. Combinatorial optimization problems are theoretically and practically very important, and we can easily describe a combinatorial optimization problem as follows. You have a finite set, we call it E, and then we call that ground set also, and we will be considering subsets of this finite set, a collection of subsets of this finite set, we call it F, and that's our objects of interest. And each subset constitutes a combinatorial object which we are interested in. And then we are given a cost function from F to real numbers, and we are interested in finding the best subset which will be optimal for us. So find X belonging to F that minimizes Cx. Of course, it could be maximized or optimized also. So this is the general description of a combinatorial optimization problem. Now we can easily see that our pedigrees are actually, any pedigree is a subset of triangles, and if we collect all those pedigrees, that is our set F, the collection of subsets of E, and then of course we have the cost function, and so this pedigree optimization problem is also a combinatorial optimization problem. There are many examples for combinatorial optimization problems, and these are actually, there are several books written on combinatorial optimization problem, and you will see some of them mentioned during this talk, and there is enough material to know about what are combinatorial optimization problems and what are different examples and how they are solved, etc. But here I'm just giving a quick review of some of the problems. The shortest root problem is one of the combinatorial optimization problem, in which what we have is a network, a directed network, and we have a point S and a point T. So we want to find out what is the shortest route through this network from S to T. So we are given distances between any 2 points in the network, so we can find out what is the shortest path in that. This is a very interesting combinatorial optimization problem. Then a maximum flow in networks. Given a network, what is the maximum possible flow of any material that can go from a given source to the sink? That's the other problem, what we call the maximum flow problem. Here again, this is a very useful problem, and in these talks I'll be considering many maximum flow problems, so that becomes a very important subroutine in our work. The next problem is a well-known traveling salesman problem, and a symmetric one, means where the distance from I to J is same as J to I. We can describe the traveling salesman problem as follows. So you are given different cities, and a traveling salesman had to, it could be saleswoman also, has to visit from hometown to all the cities and come back to the hometown. And while doing this, the total cost of traveling should be minimized. So that is the shortest or the symmetric traveling salesman problem. And this problem is one of the most often discussed problem when we discuss methods for solving difficult combinatorial optimization problem. And it has a very interesting history. Some of this we will touch upon when we proceed further. Then the assignment problem. This problem, we have some jobs and then some people who can do the jobs. We need to find out the right combination of job and person so that the total efficiency is maximized or something like. These kind of problems are often found in the area of employing people for job or employing machines for doing a particular task, etc. Then matching problem. This is given a graph. We want to find out some of the edges in the graph such that they don't have common vertices. And we want to find as many such edges as possible. So that is what is called the maximal matching problem, maximum matching problem. And this problem is also very important in combinatorial optimization problem for a reason. That is, it is a problem which was considered very difficult, and of course we then had a very efficient solution for that. So we have a lot of things to learn from the approaches given for matching problem in trying to find strategies for solving combinatorial optimization problem. So minimum spanning tree problem is another one that is given a network. It's like finding that given some places and you want to find out roads connecting these places. What is the minimum set of arcs that should be connecting so that all the nodes are connected? So that is what is called a minimum spanning tree. This is important when you are building roads, etc. All the places are connected and you are spending least amount of money to connect these places. So these problems are of very interest and practical value as well. So both theoretically and as well as practically, these problems have engaged many researchers for a very long time. So now coming to the motivation for why another optimization problem, combinatorial optimization problem, which we call pedigree, I'm explaining it now. The symmetric traveling salesman problem is a well-studied and difficult combinatorial optimization problem. And in this problem, one heuristic method is called the insertion heuristic. That means, what I mean by heuristic is not an exact mathematical solution, but it is supposed to give you good solutions easily. So people use their own, say, self-taught ideas to explore such problem. So insertion heuristic is like this. You start with a tour of a few cities, then consider the next city, find out in which of the legs you can insert that vertex or the city, so that you can now make a bigger tour, including the new city. And in this way you can go on doing until you have visited all the cities. So this is what is called the insertion heuristic. So where do you insert? You will insert where you have the cost increase the least. So this is the idea behind insertion heuristic. So our motivation to study pedigrees came from this insertion heuristic. Now I will explain how you are doing this insertion and how it connects with pedigree. For instance, take the 3 tour, that means 1, 2, 3. That is the only tour available. Now consider inserting 4. Of course, before that you can assume the cities are numbered 1, 2, 3, etc. like that. So now take city 4. It can be inserted between 1 and 2, or 1 and 3, or 2 and 3. Each one of these gives you a possible 4 tour. So from 3 tour, we are getting 4 tour. So that red tour is 1, 4, 2, 3. Now if you insert between 1 and 3, you get the green tour, which is 1, 2, 3, 4. And if you insert between 2 and 3, you get 1, 2, 4, 3, 1. That is the blue tour in this picture. So this idea is very simple. Insertion gives you from a K tour, you can get a K plus 1 tour. And this you can do until you can get an N tour. Now, where do you want to insert? It will depend on how the cost is increasing. So we have to, that is the reason I thought of, why not try to find a mathematical model that can formulate this as a mathematical problem, so that we find out the optimal places to insert 4, 5, 6, etc. So that is the beginning of my study of pedigrees. So the insertion operation, as I just now explained, I can give you a formal definition of that as it is given here. So you are actually removing one edge, ij, and then inserting 2 edges, ik and jk, by inserting k into a k minus 1 tour. So this is explained here. N is 7. You can start with 1, 2, 3, and we may go for this 4 like this. Then we have inserted 4 between 1 and 3. So we note down that we have done this insertion. Actually, you will see now the insertion corresponds to our common edge. Wherever you are inserting, that becomes the common edge, which we talked about in the pedigree. And similarly, if you insert 5 between 3 and 4, that 3, 4 becomes your next common edge that you are generating. And similarly, 6, if it is inserted between 2 and 3, you get 2, 3 as your next common edge. And finally, inserting 7 between 1 and 2, you get the common edge 1, 2. And notice that these common edges are all different. And actually, this is corresponding to a pedigree, for corresponding pedigree for 7. So this is the motivation. I am trying to solve the symmetric traveling salesman problem, but I am looking at this insertion heuristic, and I am trying to model that into a mathematical programming model. So this insertion idea is, I am going to now, suppose I insert 4 between some I and say I4 and J4, then I say the variable xi4, j4, 4 is equal to 1, otherwise 0, etc. This is how I can give an expression to our choices in terms of variables. So we can also show this as a vector of zeros and ones by ordering these edges in a particular way, we can say if the edge is selected, then you put 1 there, otherwise 0. So you get a 0 or 1 vector, and that becomes a representation of the insertion choices that you made. So we can now give an equivalent definition of pedigree as follows. So given the set of all edges for a given K, let ij be a typical edge. For instance, for E3, we can say the set of all edges for 3. That means 1, 2, 1, 3, and 2, 3. These are the possible edges. And 3 tour is the only tour possible with these edges. And that is our starting point. And then once we have a K minus 1 tour, we are going for the next one, that is K tour. So we insert 4 in 1, 2, 3. Then from that we get a 4 tour. We insert 5 in one of the edges. We get the 5 tour, etc. Like that until you get n tour. So all these choices, where you insert is what is the choice you are making. And so given a tour of n cities, we can also go backwards and find out what are the insertion decisions we made. So there is a one-to-one correspondence between tours and this, what we call these insertions. So the pedigree can be now defined as the edges which are selected for insertion, that is E4, E5, etc., En, coming from the different sets of possible edges, is called the pedigree if and only if there exists an H belonging to Hn such that H is obtained from 3 tour by a sequence of insertions. So this is an equivalent definition of pedigree, but this is what motivated me to define pedigree in the first place, as I have given earlier. And there is another important reason why I defined it in that fashion, which we will discuss at the end of these lectures, to connect what we are doing with higher mathematical subjects like algebraic topology and all that. So here I have 2 examples. So W is 2, 3, 1, 2, and 3, 4. It's a pedigree as it yields K, say for here it is 6 is the number n. So we have 1, 3, 3, 6, 4, 6, 2, 4, 2, 5, and 1, 5. These are the edges that you have in the tour that is obtained from this pedigree. Similarly, you can go through the example 2. So I promise that we will give a mathematical model for these insertion decisions. So this is actually insertion in multi-stage, so we call it multi-stage insertion formulation. Okay, because every stage we are inserting the next city into the tour. So this is called multi-stage insertion or MI formulation. We have one for the variable xi, j, k. If k is interested between I and j, in that case it takes value 1. If it is not inserted, if it is not used for that, ij is not selected for inserting k, then it takes the value 0. So we are defining a variable xij to represent the decision whether we are inserting k between I and j or not. With the corresponding to this decision of insertion, we have the cost Cijk. Now what is this cost? See, when you insert k between I and j, you are not going to have the cost for going from I to j because you are not going anymore, but you are going from I to k and of course from j to k. So you are going to have the new cost Cik plus Cjk minus Cij, and that's the definition of the Cij. So we can see that this is the incremental cost from the earlier tour to this one. So that becomes, you add to the earlier tour cost, this additional cost, that gives you the cost of the new tour. Okay? So here I have shown that MI formulation. We are trying to minimize the objective function Cijk as defined now, multiplied by Xijk. If Xijk is 1, then this cost is there. If it is 0, that cost is not going to be there. And we are summing this over all possible k and over all possible ij. Then, what are the restrictions on this? For each k, we have to select one ij because it has to be inserted in one of the edges. So, each k, we have to select one ij. That means, for each k, the sum of all ijk over all ij, which are feasible, that should be equal to 1. And this should be true for k equal to 4, etc. up to n. So these are equality restrictions. Then initially we have the 3 tour and we have the edges 1, 2, 1, 3 and 2, 3. These edges can be at the most used once by any of the k. So for each of these ij, we have to have for the xijk summed over all k should be less than or equal to 1. That means it cannot be used more than once, at the most once. It may not be used, but it can be used only once. And the next one is a very important restriction, which actually when I formulated this in 1982, it took more than a year struggling. But then once I found it, to show that it is working, it doesn't take more than 10 minutes. Okay, so this restriction number 3, what it says is that unless the edge ij is available, you cannot insert k in that. So when is it available? Only when by earlier insertion you have created the edge ij, then only it is possible. Now this could happen in 2 ways. That is, you have an edge Ri in your earlier decisions has produced an Ri. Then you can insert j in it. In that case, you get ij and rj. So ij is available in that. Another way is, then you have an isj. That means you have taken ij is coming from insertion of j between I and s. So in that case, you have ij and sj. So these are the 2 ways only you can get ij created when ij is not in the set of 1 to 3. So we can say that this sum, if it is 1 or more, then only we can have ijk. Any ijk can take value 1. Otherwise it cannot. Because if this is 0 means there is no ij, how can you insert k in that? So it's not possible. So this is what is explained there. Minus x or ij over all r going from 1 to I minus 1 minus isj s going from I plus 1 to j minus 1. This sum is actually trying to tell you whether ij is created or not. If it is not created, this will be 0, otherwise it will be minus 1. And since j can be inserted only in one place, this cannot be more than 1. So it cannot be, it can be minus 1 at the least. Next, of course, we are adding xij k over all possible k, j plus 1 to n. That means any one of them can be inserted. So that also can be at the most taking the value 1. So this plus that must be less than or equal to 0 is the constraint, so that we are sure that only when ij is produced we are inserting k, one sum of the, or we may not insert that. Finally, of course, xij has to be 0 or 1. So this gives you a 0, 1 integer programming formulation of these insertion decisions. So this formulation is a very important milestone in this research. And of course, with the definition we gave for pedigree, we can also come to the same kind of model. So let me stop here, go over the constraints, make sure they are all valid, and if any xij k, a set of xij k satisfy this, definitely that will correspond to a pedigree. And of course, that is corresponding to a valid insertion decision.